Hello everyone. Today I will be presenting our work titled Simple Economies Are Almost Optimal. This is a joint work with Amir, Shahar, Dobzinski, and Itai Ashlagi. As I am sure all of you have heard and will probably hear again in this conference, optimal mechanisms are hard to implement. An influential line of work developed simple mechanisms that are almost as good as optimal ones. Other papers approach the problem from a different perspective. Instead of changing the mechanism, change the market. This line of research starts with Bullo and Klemperer. They showed that if all n bidder values are drawn IID from a regular distribution, the auctioneer can obtain the optimal revenue of the n bidder market by recruiting a single additional IID bidder, and then running a simple second price auction instead of the Meyerson auction without recruiting the additional bidder. We explore a new market-changing approach. Consider a seller intending to auction one item. The seller can invest money and effort in advertising in different market segments in order to recruit bidders to the auction. Alternatively, the seller can have a much cheaper and focused marketing operation and recruit the same number of bidders from a single market segment. Is the simple marketing strategy good enough for the seller, though? So in our setting, the market contains a vast number of buyers, and the seller has the budget for a marketing operation that recruits exactly n bidders. The market is divided into m populations or market segments, representing, for example, nationalities, age groups, occupation, or any combination of those of the above. The seller knows the value distribution of the members of each population, and each population consists of many potential buyers whose individual values are drawn IID from the distribution of the population. The seller can choose any combination of n bidders. Multiple bidders can be selected from the same population, and even all bidders can come from one population. Our goal is to compare the simple and focused marketing strategy that recruits all of the bidders from a single market segment homogeneously with the optimal yet complex marketing strategy of handpicking each bidder from across the market and different market segments. How much revenue do we lose by choosing the simple solution rather than the optimal one? It is not hard to see that sometimes no homogeneous mechanism can extract more than half of the ideal revenue. Consider a distribution that returns the value 1 with probability 1, and a distribution that returns the value 1 over n epsilon with probability epsilon, and 0 otherwise, for some very small epsilon. Note that the revenue is at most 1 if you choose the values of all n bidders to be drawn IID from the constant distribution, obviously, or the values of all n bidders to be drawn IID from the second distribution, because the probability that one of the bidders will not be 0 is at most n epsilon. The ideal revenue is very close to 2, and it can be obtained by taking one bidder from the constant distribution and the remaining n-1 bidders from the second distribution. To attain a revenue of 2 on this economy, we run a second price auction with a reserve price of 1 for the constant value bidder and a reserve price of 1 over n epsilon for the remaining bidders. So this gives us an immediate bound on the attainable revenue we could hope for. Now, our setting more formally includes one item and a set D of m distributions, each representing a population of the bidders, or a market segment. An economy E is a set of n bidders, each drawn independently from some distribution in the set D. An economy is homogeneous if the values of all bidders are drawn from the same distribution. Rev E is the revenue of the optimal auction over economy E. The ideal revenue opt is equal to the maximum over possible economies E of the revenue of economy E. That is, we consider the revenue obtainable from all possible combinations of bidders, and opt would be the revenue obtained from the best such combination. Now, our main result shows that it is always possible to extract a constant fraction of the ideal revenue using a homogeneous economy. So our theorem states that for every set D of distributions, there exists a homogeneous economy E, where the values of each bidders are drawn independently from the same distribution in the set of distributions, such that the revenue of an optimal auction for E is at least half times 1 minus 1 over E fraction of opt, which is approximately a third of the attainable revenue. Recall that earlier we have shown an upper bound of half for this ratio, so we established that homogeneous economies can always extract a constant fraction of the ideal revenue, and that sometimes they cannot do better. As a nice additional bonus, beyond the fact that economy E is simple by being homogeneous, the action for E that we use to obtain this bound is also simple. It is a second price auction with a reserve price. Now, the mechanism designer it could be unable to freely choose an auction format. Our next set of results that we now show consider situations in which the mechanism designer is constrained to use a second price auction in all economies, either because it is not allowed to tailor a mechanism based on the specifics of the distribution, or because of the simplicity of a second price auction. SP Rev E is now the second price auction revenue, and the ideal second price revenue is the maximum revenue, analogously to our definition of opt in the previous result. We prove that homogeneous markets also approximate well the ideal second price revenue. So we show that for every D, there exists a homogeneous economy such that the revenue that can be generated by a second price auction in E is at least a constant fraction of the ideal second price revenue for a constant that is approximately 0.108. Next, we consider whether being able to recruit bidders from a small number of market segments, in contrast to just one, as in homogeneous markets, allows us to significantly extract more revenue. We show that is indeed the case, at least when restricted to the second price auction. This theorem shows that for every constant epsilon larger than 0, there exists a simple economy that uses only a constant number of distributions, irrespective of the number of bidders n and the set of distributions d, and extracts almost all the ideal second price revenue. So this function fe, the number of distributions that we need to get the 1 minus epsilon approximation, is a function of just epsilon. So if you want 90% of the revenue, you need, let's say, 20 distributions. If you want 99%, you'll need more, like 200 distributions. These numbers are not the real numbers. The real numbers are larger. But the point is that it doesn't matter what the input set of distributions is, nor the number of bidders. Related work. Our work is related to the team selection problem introduced by Kleinberg and Ragu. In this problem, you are given n candidates modeled as random variables x1 to xn, and the goal is to choose k team members with no repetition, so as to maximize the expected sum of the highest h values. They show a constant factor approximation for this objective function. However, we remark that maximizing the sum of the highest h values for any h does not imply a bound on the expected second highest value. A follow-up work by Meta, Nadab, Solmas, and Rubinstein consider the variant of the problem with bidders instead of team members, where the goal is to maximize the revenue of the second price auction. Meta et al. Showed that it is NP hard to approximate this objective within any constant factor. Here it is important to note that our setting allows repetition in bidder selection. That is, we can select several copies of the same bidder. This distinction allows us to approximate the second price auction revenue using a homogeneous economy, which is also polynomial time computable. Just try all possible homogeneous economies, while a similar simple approximation is not possible in the context of team selection. We now prove our main theorem, which shows that a homogeneous economy generates about a third of opt. Let the random variables x1 to xn be the optimal mix of n bidders. We will show that taking n copies of one of these random variables generates the desired fraction of opt. We start by defining a threshold h on the values of the bidders. To find this threshold, we consider the CDF function fi of each bidder I, and we define the threshold h to be the maximum value of the inverse of fi evaluated at 1 minus 1 over n. This is easier to understand visually. Put all CDF functions in one chart and look at the horizontal 1 minus 1 over n line. Draw a perpendicular line at the intersection point with each CDF, and the rightmost value indicates the value of h. We now split into two cases, depending on whether the winning bidder exceeds the threshold h or not. The first case is when the instances in which the winner is below threshold contribute most of the revenue, at least half opt. Note that by definition of h, the corresponding maximizer, denoted I star, has value at least h with probability exactly 1 over n. Now, it is always true that the revenue is upper bounded by the winner value, since we are individually rational. In this case, the winner value is upper bounded by h, but the revenue is at least half opt in expectation, and thus h is at least half opt. Now, we run the following auction. Take n copies of bidder I star, defined below in blue, and run a second price auction with reserve price h. The revenue is at least the probability that the item is sold times h. The sale probability is 1 minus the probability that all agents are below threshold, which is equal to the term in parentheses by definition of bidder I star and the equation in blue below. And h is lower bounded by opt over 2, as we have seen above. Simple calculation now yields the desired result, finishing this case. The second case is when most of the revenue is gained from instances where the winner has value greater than h. We start by truncating all probability distributions, rounding down sub-threshold values to 0. Now, clearly no revenue is lost from the high-value instances, since the winner value is above threshold h and thus stays the same. So we can still sell her the item at the same price we had before the truncation. Now we denote the economy E tilde, the truncated economy. The revenue of E tilde can be split into a sum of RIs, where RI is the expected revenue gained from bidder I. Since in the truncation we lose none of the revenue of instances with a winner exceeding the threshold h, and such instances contribute at least half of opt, the revenue of E tilde must be at least half opt. Now the sum of RIs has n summoneds, so there must be one summoned and one bidder j, such that Rj is at least opt over 2n. Consider the single-player optimal auction with this bidder j alone. This is a take it or leave it auction with price pj and sale probability qj. Clearly, the revenue of this auction qj-pj is at least rj due to the auction being optimal. And by our choice of j, we have that rj is at least 1 over 2n opt. Moreover, qj is at most the probability that bidder j is non-zero, which is upper bounded by 1 over n due to our truncation. We now run the following auction. Take n copies of bidder j, run a second price auction with reserve price pj. The revenue of this auction is at least the probability the item is sold times the reserve price. The probability of selling the item is 1 minus probability that no bidder is willing to pay pj, which by definition of qj is equal to 1 minus qj to the power of n. The next transition follows from a simple calculus argument using the fact that qj is upper bounded by 1 over n. Now we have a well-known bound of 1 over e. And finally, we plug in our inequality for QJPJ obtained by definition of bidder J. This proves the theorem. To recap, our setting consists of a seller of a single item choosing a combination of n bidders from a set of populations to maximize revenue. Our first result showed that homogeneous economies give a constant fraction of the revenue, and it's about a third of the revenue. And we have also seen that this fraction can be at most half. The second result shows a similar guarantee when we are restricted to using the second price auction, and the number is around a tenth of the revenue. And finally, our last result shows that selecting the bidders from a small number of distributions can get you arbitrarily close to the ideal second price revenue. We have several open questions. So what is the tight ratio obtained for homogeneous economies? We suspect that the upper bound of half is tight, but we don't have proof of that. And what factor can we achieve with 2 distributions or 3 distributions or so forth? And can we approximate the optimal revenue arbitrarily well using few distribution? That is, provide a similar result to the last theorem without the restriction to the second price auction. Thank you everyone for listening.